Morning, everybody, and welcome to this screencast on what is called binomial distributions. So in order to start this off, it would be most appropriate for us to list the different types of distributions and then to qualify or classify what is a binomial distribution. All right, so just to recall, if you have a look at the opening here, it says that a probability distribution is a table, formula, or a graph that gives the probabilities for all possible values for a discrete random variable. Okay, so we've been working with determining probabilities of specific events, and this is nothing more than a collection of those events filled out through a table, expressed as an algebraic formula, or as a graph. So the different types of distributions are as follows. So there are four particular types that we'll look at in this course. So today the focus is on something called a binomial distribution, and that'll be followed up by geometric and hypergeometric distributions. And then a little bit later in the course, we're going to come back to look at what is known as a normal distribution. Okay, so when you start working with different problems that require a binomial distribution, there are a few things you need to keep in mind. So when you are writing a particular test, say for example, usually there's one answer to a closed problem. Okay, and a closed problem is one that simply has kind of a yes, no, true, false, right, wrong type of answer to it. Okay, it's not an open problem. So these types of questions, what you want to take note of is the following. Okay? So in the context, the outcomes of being correct or incorrect, as there are only two, form what's called a binomial event. So we work with binomial events, right? So A and B. So what is the probability that this and that would occur? Okay, and in some of those cases, the event involved, right, true false questions, the outcome of rolling an even or an odd, that type of thing. The outcomes arise as a result of something called a Bernoulli trial. So Bernoulli is the name of a mathematician, scientist from many days past. And those trials are specifically classified as independent trials. Okay, so that's really important to remember. Independent trials that have two outcomes. So we often talk about those outcomes as success or failure. Okay, so you'll see a variety of texts that use those terms to describe the outcomes for a binomial experiment. Okay, and Bernoulli trials are a property of those types of experiments. So moving forward, the best way for us to tackle this is to take an example from the past that we've wrestled with and now apply some of this thinking to that example. So prior to that, we'll do a real quick assessment here, and I would encourage you to pause the video and think these through. So part A, getting tails 4 times on 10 tosses. Is that a binomial event? Right? So if it is, then what we'll notice is that there should be two outcomes. Okay? So there are two possible outcomes, and of every 10 experiments or trials of that experiment, the results, okay, the experiments are exactly the same. Right? And any toss doesn't depend on the result of another. So they're independent and identical. Okay, so that's a key feature. So if you go back and look at the definition, so you have to have two outcomes. The outcomes must be independent. Okay, and those particular trials are identical. Okay? The next one, rolling 3 5s out of 15 rolls of a 6-sided die. So for that one, we likely said yes, because of the fact that we're only interested in rolling a 5 or not. So success is rolling the 5, failure is not. There are two results. Okay, so it is a binomial event, and each of the 15 roles, they are identical in nature, and one role is independent of the other. And last but not least, rolling 3 5s or 3 2s, that one is a clear case of no, okay, as there are 3 possible outcomes, 5, 2, or some other number. So looking back, you can see that it is not a binomial event, as there are 3 particular outcomes. Okay, so we can't define success and failure on the basis of having those 3 outcomes. Okay, so that's really important. So moving forward and through that lens of those examples, let's try this one out. Okay, so if you're using the template off the course website, you might notice that the table here got cut off. So I would encourage you just to add on to that. So the example starts out with the die being rolled 3 times, and we're looking for the probability that the first roll is 5. Okay, so first roll is 5. So down below, what we'll do is we'll designate the probability of the first roll being 5. There are 6 possible outcomes, of which there is one we're looking for as a success. The probability that the second roll is not 5 or the third, these are important as well. Okay, because we are rolling the die 3 times, okay, we have 2 outcomes, the experiments are identical, okay, and as well, each particular trial is independent of the next. So we're looking for also the probability that the second and third rolls are not 5s. Okay, so those are also important to consider. So on the basis of that, our probability calculation would be as such. Okay? So we're interested in the probability of roll 1 being 5 and, right, that's a critical word here when we're talking about independent trials. Roll 2, not 5, and roll 3, not 5. So as we've done previously, when we have independent events, we ended up multiplying those together. Okay, so 1/6 times the square of 5/6. Now, I'm not going to evaluate that. I'm going to leave the expression as it is, as we're not really after a particular final value. Okay, I think it serves a good purpose to leave it in that raw form so we can see as we move forward and extend the example how patterning will become very helpful in terms of generating a rule for binomial distributions. So carrying on with this one here, part B is asking us to determine the probability that the roll of 5 will appear in any of the 3 available positions. Okay, so it's not just placing a 5 in the first position, but you can see how we are questioning the position of the 5. Okay, and what's really key here is this notion of available positions. Okay, we know that the order isn't going to matter, okay, and where that 5 goes. So the order is not relevant, but we are looking to arrange those, or that 5, order not important, which is going to imply that there will be multiple probabilities to consider, and there will be different positions in which the 5 will go, and that is going to involve the use of combinations. Okay, so as mentioned previously, throughout this unit, we'll come back and keep considering the notion of combination. So let's see how that's going to play out. Okay. So let's start here. The number of ways that a single 5 goes into the table, okay, because of those 3 positions, those 3 roles, means that it's the same as the number of combinations of 3 items, choosing one at a time. So there are 3 choose one ways of placing the 5 in the table. Okay. So because of that, the probability of getting the 1 5 in the 3 trials is going to be, okay, 3 choose 1 multiplied by, check this out, remember what we did down here, it's the probability of the first roll being 5 was equal to this. Okay. Now we're extending it so that the roll of 5, that value of 5, can actually occur on any of the 3 rolls. Okay, so 1, 2, and 3. So that implies that there are 3 choose 1 ways of assigning the 5 into any of those positions. Okay, so we have to triple. Okay, 3 choose 1 is equal to 3. So that would be times 1/6 to 1 times 5/6 squared. So moving forward, let's keep extending this because the notion is about studying probability distributions in this unit. So that implies that we need to consider all possibilities, whether it be no 5s, 1 5, 2 5s, or all 3 rolls being 5s. That would constitute a probability distribution. So let's have a look at what would happen with 2 5s. So you can see how in the table, okay, we have roll 1 and roll 2 occupying or having 5s occupying those positions, and roll 3 not being equal to 5. So what that means is that the probability of roll 1 being 5 is a sixth, roll 2 is a sixth, and then the last one, okay, which is not 5, would be 5 on 6. Okay. That's a little bit different than what we had before, right? Right now, if we simplified that, that would be 1/6 squared multiplied by 5/6. Okay, so let's continuously check out what happened before. So beforehand, take note of what we had, right? The powers were 1 and 2 because of the number of successes we were looking for. So this here, this exponent, this corresponds to the number of successes. Okay, whereas this one here would be the number of failures. I'll just call it failure, I'm running out of space. Okay. Also notice where the number 1 comes up, it's also here, okay, in terms of our combination. So let's go back to what we just did here and notice that this time things have changed a bit. We now have 2 successes, and here we have 1 event which is or constitutes failure. So because we're trying to fill in 2 positions of the table, and it can be any 2, order not important, combinations becomes important. In fact, because we have 3 positions to fill, and we're looking for placing 2 5s, notice that 3 choose 2 then becomes the multiplier for our probabilities. That 2, of course, the number of successes also appears here. So let's review here in total, right, for this particular situation. Let's see if I can increase the font size on that. Okay, just give me a moment here. I'll see if I can do that. There, that's a bit better. So having a look at the text that we have, so that's starting here. The number of ways the 5s go in will be 3 choose 2 ways. And then below you can see the expression that represents that. Okay, so 3 choose 2 is going to extend that a bit. 3 choose 2, if you were to calculate that by formula or by some other means. Another means could involve Pascal's triangle. So I'm just going to show you a visual I found online at this particular website. You can see how each value has its corresponding combination form. And you can see that 3 choose 2, which is here, is equal to 3. And we had already used 3 choose 1 for placing that 1 5. So That's another trick too, is to save yourself some time in calculating or not using your calculator. You can have a copy of that diagram to help you out. So moving back into where we were, let's go full screen on this. So 3 choose 2 is equal to 3. So that probability would be 3 multiplied by 1/6 squared multiplied by 5/6. So last but not least, let's go ahead and complete the probability distribution. Okay, so all of these individual calculations, let's summarize them through a form of a table. Okay, so we've already done this one, right? That was the first scenario where we were looking for 1 5, which constitutes 1 success. We just did this one, right? 2 5s or 2 successes. So it makes sense that for no 5s, we'd have no successes. And then for placing all 3 5s, that would constitute 3 successes. Okay. So what we have now in the form of a table is a probability distribution. Okay. You could write this in horizontal form to make it look like an expression, right, that would have come from an equation. Or you can represent it as a graph. Okay, so what you could do is convert each of these using your calculator or some form of software to a fractional or a decimal value, and then plotting them on a graph. So that's the next piece, is let's have a look at this visually in terms of a graph. So here's a sample that I created in Excel, simply by, as you can see down here, I calculated the decimal representation for each of the probabilities, and then I placed them into the table, okay, into the chart. And you can see that the number of successes are here, okay, and the relative frequency of the probability here, okay, of course, is represented there along the vertical axis. Take note, though, that when you are setting up your distributions, is to look at the shapes. Okay, so the shapes of the distributions convey a lot of meaning. Okay, so if you take a look at this, you can track this back to the calculations. So for instance, the most probable scenario that we have, okay, in terms of success, is that of not placing any of the 5s. Okay, so for no 5s, we have a relative frequency of almost 0.6. Okay, that makes a lot of sense, because if we go back and we look at the makeup of the distribution of the formulas, right here in this first row is where we have no successes occurring. Okay, so there are 0 successes. So notice that the probability, okay, so 5/6, this fraction here, very close to 1, isn't it? So it's approximately 1. It's off by a sixth. And if you cube something that is close to 1, then the value you get is an answer closer to 1. Okay, and what that means is that every time we reduce, okay, the value that has the greatest impact on the calculation and increase this one, we're going to start to see the values moving away from 1. Okay, so we're going to see the answer starting to draw itself away, right? It's going to move away from the value of 1. And we know that in total, right, in sum, as those values decrease, that the sum of the probabilities, right, the sum of all p at x, because really that's what this is p at x, is going to be equal to 1. Okay, so keep that in mind. Between 0 and 1 are the sum of all the probabilities for any probability distribution. Okay. And there is some patterning through the values, simply because of the effect of the number of successes you have and the weighting that's assigned to the successes. Okay, so the weighting for success and failure, right, in this case, you can see how they're weighted differently. Every question is going to be a little bit different. So not all distributions will have the same look. Some will be very characteristic in their shapes, and others will be variant upon the weighting assigned. So what is the fraction or percentage for success and failure? That's something to keep in mind, as well as the number of successes. Okay. So this particular graph you can see has a really interesting trend. It's falling from left to right. Okay. Not necessarily a linear relationship, but we'll see as we look at other distributions more nonlinear. This one, in fact, is something called a skewed distribution. Okay, and in fact, it is not only skewed, but it is what we say right skewed or positively skewed. And that's because of where the tail is. Okay, so you can see these smaller values. This particular graph tends to the right to have smaller values, whereas the larger ones are on the left. So this is referred to as the tail of the distribution. So if the tail is on the right or is positive, that is to the right of the other values, and we refer to it as being right skewed or positive skewed. Okay. Last but not least is no particular distribution would be complete without specifying the formula. Okay. So a formula that is in general for this situation is if you're looking for the distribution of all events X, that was the roll of a 5, or having 5 rolled as a success. R is the number of successes. And as you move your way through, 1 on 6 was the probability, so the probability of success. 5, 6 was the probability of failure. Okay, and of course R again is the number of successes. So you'll notice that as the value of R, okay, increases, okay, then the value of 3 minus R would decrease, and vice versa. Okay, so there's a lot of patterning here. So when you are solving problems that involve multiple probabilities for the same distribution, you can really rely upon that patterning. So out of your textbook, I copied these 3 pieces. It's from around page 299-ish, somewhere in that range. So have a look at these. So these are the general formulas for binomial distributions. So you can see how this one here very much mirrors the one that I just showed you, but this is in general, okay, for any scenario. So the only differences here is that they use K instead of R. Okay, so take note of that. P is the probability of success. So P of success. And then they use 1 minus P. Right? 1 minus P, again, that's the complement. So complementary to the probability P. So 1 minus P, that constitutes the probability of failure. And also what you want to note is that in other texts and online, they will refer to that value as Q. Okay, so 1 minus P is equal to Q. The expected value, okay, if you look below, this is now becoming more of a common formula for us. So you take the distribution. So here are the probabilities from your distribution, and we end up multiplying those by the value that we're seeking. Okay. So expected value is like the average or the mean of a distribution, and you can calculate it that way. But very simply and easily, this is convenient. We don't have a proof for this in our course, but we could look that one up. But E of X is nothing more than NP. So if you take the number of trials and you multiply it by the probability of success, you're going to have the expectation. Okay. So before you sign off on this video, definitely take some time to consolidate your thinking. And what I would encourage you to do, okay, I'm just going to scroll that here, would be one is for this example, have a look at the expected value. Okay, what do you think it is? And then try to calculate that. And another thing too is if you go into the practice problems, which are not being assigned at this time, they are on the course website. Take a look at number 5. So before you walk away from this, or before you come back to class, take a moment to refresh your memory and review. Number 5 is very similar to this question here. So it would be a great time and opportunity for you to apply what you are working to learn through this screencast.